Alright, so last time I introduced to you the partial derivatives of multivariable functions. And so we did a few simple cases, and so now this is sort of the second set of that. We're going to be looking at slightly more complex cases where it would involve maybe our chain rule and some of our other rules. Alright, so this first example here, 3x squared y cubed times, or plus 3 times the natural log of xy. And so this is the part where I have to use my chain rule on my natural log. Alright, so the derivative with respect to x, and then with respect to y. So the x part's the function part. Everything else is just considered a constant. Right, the y parts are constants. Alright, so in this first piece, this is the function part. The 3 is a constant, the y cubed is a constant. So they behave the same way. 3 comes along, the y cubed comes along as a constant multiplier. I take the derivative of x squared using my power rule, that's just 2x. And there's the derivative of the first piece with respect to x. Alright, now the second piece is where I'm going to have to use my log rule and my chain rule. 3 is just a constant multiplier, it comes along. The derivative of the natural log is 1 over the function inside. So 1 over x times y. But remember, chain rule is, I'm not done yet, then it's times the derivative of the inside part. I'm taking the derivative of the inside part with respect to x. So the derivative of x is 1. The y is a constant multiplier, it comes along. And so the derivative of xy with respect to x is y. It would be technically y times 1, but we just write down y. Alright, I am going to clean this up. I'll multiply my 2x times my 3 to get 6x y cubed plus this y reduces with that y. And then I'm going to rewrite this as a fraction. 3 times 1 is just 3 over x, and so there's the derivative of that function with respect to x. I'm going to do a very similar thing now with respect to y. Alright, so now y is the function part. Everything else is considered a constant. And so in the first piece, the y cubed is the function part. The 3x squared is a constant, and so it just comes along. I take it times the derivative of the y part, which the derivative of y cubed is 3y to the second. Alright, there's the first part, plus the derivative of the natural log with respect to y. So 3 is just a constant, it comes along, 1 over the function inside. So the first part of that's the same. The part that's going to change is when I take the derivative of the inside. I'm now taking the derivative of the y. The derivative of y is 1. The x is a constant multiplier, and so it would be x times 1, which is just x. Alright, then I clean that up. I'm going to take my 3 times my 3 to get 9 out front, and then the x is reduced, and so this function simplifies to 9x squared y squared plus 3 over y. Alright, next one. So again, a little more complicated function. I've got x times y squared times e to the 2x. Alright, so I've got an e term and a 2x, so chain rule on that. And so when I take the derivative with respect to x, so the derivative with respect to x is the more complicated one because there are two x parts. There's this x out front, and then there's this e raised to the 2x. And so I am going to have to take, when I take the derivative with respect to x, it's going to be a product, and then the e term requires my chain rule. Alright, now the y squared, I can pair the y squared with whatever I want, but I'm going to pair it with the x since the e is already complicated enough. So y squared is going to be paired with the x part, and then e to the x squared is going to be the separate function. So those are my two functions. Alright, product rule first, right? First derivative of the second plus the second times the derivative of the first. Alright, so the first function, xy squared times the derivative of the second, which is the e term that requires my chain rule, so e to the 2x, but I'm not done yet. There's a times 2, right? So e to the 2x times 2 is the derivative of the second, plus the second times the derivative of the first with respect to x, right? And taking the derivative of that function with respect to x. Y squared is just a constant multiplier, it comes along, the derivative of just x is 1. And so there's the derivative of that function with respect to x. Now I am going to clean it up. First of all, I can factor out a couple things. I've got a y squared in both terms, and I've got an e in both terms. So I'm going to pull out my y squared and my e to the 2x. What's left over is, in the first term, I've got a 2x left over, and in the second term, 1 is left over, right? When I factor everything out, I'm still left with a 1. So y squared e to the 2x times 2x plus 1. And there's my derivative simplified with respect to x. Alright, so the derivative of this function now with respect to y is actually easier, because if you look at it, there's only one y part, just the y squared in the middle. So this y squared is the only part that's the function. That's the part I'm taking the change, the derivative of. Everything else is constant. Ugly, unknown constants, but they're constant. X is being held constant. Therefore, this x is just a constant. E to the 2x, because x is being held constant, is also an irrational constant, but it's a constant. And so the x and the e to the 2x comes along. The only part I'm taking the derivative of is the y squared. Right, the derivative of y squared is 2y, and it's fine if you leave it like that. We like to rewrite it with the 2y in the front, and then I like to order x first, then y. And so I'm going to simplify it to 2xy e to the 2x. But again, that is a minor thing. If you left it like this, that's fine. Alright, the next example. Alright, so it's my function, 3x squared y plus 5 raised to the 3 halves. And so chain rule, because the outside is a power. Alright, so this is just chain rule. Alright, first the derivative with respect to x, and then the derivative with respect to y. Well, remember the chain rule on a power function is, well, I take care of the power. First thing I do is I pull my power out front, so the 3 halves comes out front. Take my group raised to 1 degree less. Well, 3 halves minus 1 is a positive 1 half. The group inside stays the same. Alright, then separately, and separated by multiplication, I take the derivative of the inside with respect to x. Alright, so the derivative of the inside with respect to x, so x is the part I'm taking the derivative of. The 3y comes along, they're constant multipliers. I take the derivative of x squared, which is going to give me a 2x, and the derivative of 5x, which will give me a plus 5, which again, I'm going to clean this up a little bit. If you want to leave it, that's, again, that's a minor thing. Alright, I can take my 2x times my 3 to get 6xy plus 5. Alright, so there's my derivative with respect to x. Alright, now my derivative with respect to y. Alright, so derivative with respect to x, derivative with respect to y. Well, the outside function's the power on my group. And the power on my group, it doesn't matter if I'm looking at x or y, it behaves the same way. Alright, my power rule. So the very first part of this is identical to the derivative with respect to x. I pull out my power 3 halves, take my group without changing a thing about my group, and raise it to 1 degree less, 1 half. The part that matters, which variable I'm looking at, is when I take the derivative of the inside. Alright, the derivative of the inside, now I'm looking at the y, and so this is the only y variable. Alright, I'm taking the derivative of that y part, that's the part that's changing. Everything else is constant. Alright, so the 3x comes along, 3x squared comes along. The derivative of just y is 1, that would be 3x times 1. And then the 5x zeroes out, and so the derivative of that is just 3x squared. Alright, so again, the beginning parts are the same. It's the times the inside that's different. It's the inside part that matters. Alright, that's going to be true about when we just have a power rule. Alright, same thing's going to happen in my next example. Alright, this is going to be my chain and my e term. Alright, e raised to that x squared plus y squared minus 6x. Alright, the derivative with respect to x. Well, remember the e term, the derivative of the e is itself times the derivative of the inside, alright, the power part. And so the first thing you write down is the original expression without changing a thing. Then separated by multiplication, we take the derivative of the inside with respect to the variable I'm looking at. So I'm looking at x, and that's the only term with x in it. Everything else will zero out. And so the derivative of x squared is times 2x. Alright, so there's the derivative of that function with respect to x. Alright, now with respect to y, well, the first step's exactly the same. Write down the e term without changing anything about it. Alright, but then you're not done yet. The chain rule is I take it times the derivative of the inside. Now it matters which variable I'm looking at. I take the derivative of the y parts. Alright, there are two y parts. There's the y squared and the negative 6y. So I'm going to get negative 2y minus 6. Alright, is that part. And there's my two derivatives for my g of xy function. Alright, my next example. Alright, so again, this one's just more complex. There's a lot more moving parts on this one. It looks like the x variable is a little more complex than the y because there's more x terms. So derivative with respect to x. Every single value, every single term in here has an x value. Alright, so the derivative of each of the parts with respect to x. So 4x cubed is just the power rule. 12x to the second. Alright, remember taking the derivative of the x part. The 5, the y squared are constant multipliers, they come along, so 5y squared comes along. Derivative of just x is 1. Alright, taking the derivative of the x cubed part. Alright, the derivative of the x cubed is 3x squared. The y to the fourth comes along, and if you had written that the other way around, that's fine. You could have written y to the fourth times 3x squared. Perfectly fine to do that. Alright, then the last one, e to the 2x, that is going to require my chain rule, e to the 2x. You're not done yet. Don't forget the times 2. Alright, there's no like terms, there's nothing to factor out, so I'm just going to leave it. So there's my derivative of that function with respect to x. Right now my derivative with respect to y. Now as it turns out, the y part's a little easier, because if you look, there's only two y expressions, meaning that'll zero away and that'll zero away. And so I just take the derivative of the negative 5x with respect to y. So the negative 5x comes along. I take the derivative of the y part. So the derivative of y squared is 2y. Plus the second term, the x cubed, comes along. I take the derivative of the y part, which is y to the fourth. So I'm going to get 4y cubed. All right, and then I will clean this one up a little bit. Negative 5 times 2 is negative 10xy. And then I just like to move my constant to the front. So 4x cubed y cubed would be my simplified version of that. Alright, so there's my derivatives with respect to both of my functions. Values. My first order partial derivative with respect to each of my variable parts. There we go. Alright, the next example. Alright, so I've got my natural log of x squared, y squared. So this is going to be my chain on my natural log, if you can read that. The chain and the natural log. Alright, so the derivative with respect to x. Well, the derivative of my natural log is just 1 over the function inside. So 1 over x squared plus y squared, but then I'm not done yet. The derivative of the inside, now it matters what variable I'm looking at, right? The inside's derivative is where it matters. I'm taking the derivative of the x part, so the x squared's derivative is 2x, the y squared will 0, and then I'll write that as a single fraction. 2x over x squared plus y squared. Well, the derivative with respect to y is almost the same, only one part changes, right? The beginning is the exact same. The derivative of the natural log is 1 over what's inside times the derivative of the inside, but now I'm looking at the y variable. So the x squared zeroes out, so I'm looking at the y squared. So what changes is instead of 2x, this is now 2 times y. Alright, so again, they're very similar, but there is a subtle difference to it. Alright, the derivative with respect to y is 2y divided by the x squared, y squared. Alright, so the last part of this note is find the value of the first order derivative at the given point. So f sub x at, so I'm looking for, and I think this is what's in your notes, f sub x at negative 4, 1. And f sub y at negative 4, 1, which means I'm going to find my first order derivative and then plug that function into it. And what you're going to see is I am going to get two different rate of change. All right, my function changes differently in the x direction than it does in the y direction. All right, so we'll start with x. The derivative of this with respect to x. So the derivative with respect to x is going to give me a 12x squared minus 10y. That part zeroes out. Plug my point into that. So again, negative 4 goes in there for x, 1 goes in there for y. So make sure you're careful. Negative 4 squared, make sure you put parentheses around that so that you get rid of the negative. And so this comes out 182, which means f of xy, the original function, is increasing by 182 units per change in x, whatever x represents. That's how it's changing. All right, so it's moving up by 182 units as x changes. All right, now the y direction. All right, so the derivative with respect to y, and then we'll plug in our negative 4, 1. All right, so now I'm taking the derivative of the y parts, so negative 10x plus 8y to the third, and then I'm going to plug in my point, negative 4, 1 into that. So negative 10 times 1 plus 8 times negative 4 cubed. All right, comes out negative 48. All right, so this means in the x direction it was moving up at 182 units per change in x, but in the y direction it's decreasing. All right, my original function f of xy, its rate of change, is a decrease by 48 units per change in y, whatever y would represent. So y would represent something, so maybe x represents big tables and y represents small tables. All right, so my profit would increase by $182 when we change the small tables, or my profit would decrease by $48 when I change my large tables. All right, so again, it represents some type of change depending on what my variables are. All right, and so that finishes up first order derivatives and practicing those. The next set of notes is going to be second derivatives and how we find those. All right, so we'll stop there for now.